Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series, and I am delighted to have Amber Young with us today. Hello, Amber.
Hey, hi, thank you for having me.
Well, thank you for agreeing to talk about your very awesome article, which we'll get to here shortly. Let's see. And Amber, what's your geolocation? Where are you at?
Yeah, so I'm calling in from Greenbelt, Maryland right now, particularly NASA Goddard Space Flight Center, where I
Very
work.
cool. Very nice. Let's see. It is May 14th of 2025 as we record this. Is summer happening on the East Coast yet? Are we still kind of in our spring mode, transition? Where are we at?
Well, the temperatures have definitely been summer-like. I'll say for the past couple of days it's been rainy, so
Oh, because you get the humidity with it too. Yes.
yeah, yeah.
Indeed. So I'm in Phoenix and we are definitely rolling into our summer months and we don't quite have that humidity of the East, but we do get the haboobs and the winter storms rolling in. And I think you were at NAU when you did this. Yeah, you've been at Flagstaff.
Yes.
Yeah, yeah.
Yeah, Flagstaff.
But they don't get haboobs, right? Like Phoenix does. So very cool. Very cool. And Amber, what do you like to do for research?
Well, so I mainly do exoplanet characterization. I use a suite of atmospheric modeling tools and statistical analyses like retrievals, which I'm sure we'll hear about more. But I use those tools in order to study exoplanet atmospheres, particularly in the realm of biosignature detection and really understanding like what can we search for on exoplanet atmospheres in order to state whether or not there's a likelihood that planet might have life.
It's a hot topic these days.
So-
Very cool. And that is going to bring us to this very awesome PSJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. Retrievals applied to a decision tree framework can characterize Earth-like exoplanet analogs. And Amber, take us away.
Yeah, thank you so much. To start off, I just want to thank all of my co-authors listed here in terms of Jamie Krause, Jada Arney, Sean Donegal Goldman, my PhD advisor in particular, Tyler Robinson, and Sandra Bastelberger. We're all amazing collaborators of this work. Special shout out to Jamie Krause, who's a graduate student at Johns Hopkins University now.
Very,
Um,
very cool. Yeah,
yeah.
all right. NAU, you were at NAU. Yes, I knew I read that right.
Yes.
Very cool. Very good. Good shout out, too. Good shout out. Okay, let's get into it. Let's go.
Yeah, of course. So the main motivation behind this work is really looking at the next steps for exoplanet characterization. We've been in this realm of exoplanet detection, where a lot of different strategies, like the transit method, have been very successful in telling us how many planets are out there, general characteristics about whether or not they're Jupiter-like
Okay.
versus terrestrials, and really just kind of going through the counting process. How many of each type? What's the diversity of planets that actually exist out there?
Right.
And now we're really approaching an exciting time in exoplanet science where we can take the extra additional step to say, well, not only are the planets there and that they exist and they're plentiful, but also start to ask questions about what are their atmospheric characteristics
There you
in
go. Cool.
particular, and really just honing in on this question and the search for life. Like, how can we search for life through those atmospheric signatures, which are
Mhm.
called biosignatures?
Very
And so a lot of this work is motivated by mission prep for the next generation NASA mission that's a
cool.
follow on from the Decadal Survey recommended mission called the Habitable Worlds Observatory.
Yes.
Um, so this is like I said, a decadal recommended mission that is planned for, maybe a couple decades out in terms of launch date. But we're really thinking about now,
Right.
how do we make the most efficient observations with the observatory, and what are the actual scientific objectives and scientific drivers for the mission?
Cool.
Um,
Very cool.
So it's really exciting. HWO, if there were ever a dream mission, HWO would be my dream mission because it has explicit goals to do and conduct a robust search for life
Cool.
on potentially Earth-like planets
Yep.
that are orbiting sun-like stars.
Okay. Very cool.
Yeah, yeah. So in in a sense, you know, a lot of this work is again motivated by the actual strategies that we might take, how we might conduct these observations, and making it such that the each observation that we get is both fruitful with information, robust, providing enough evidence and contextual information to be able to ask those questions of
Yeah.
life determined and diagnostics versus also being able to balance the efficiency of those observations. Because you
Right.
know, for high priority targets and a limited mission lifetime and duration, we need to really use and plan our time wisely to be able to dedicate enough time to the high priority targets and really, you know, just do a robust search and a robust sweep of all the targets that we have.
You should be HWOPI, man.
Oh, well, I am a
You
project
did that
scientist.
really well.
No, I mean it is really exciting. So in
Yeah.
terms of like HWO in and of itself, the project office is based out of NASA Goddard,
Mhm.
and the interim project scientist is actually co-author on this work, Jada Arney. She's a really close collaborator of mine, and was on my PhD committee back when you know I was still in school. So she
Cool.
is interim project scientist of the mission. So I feel
Nice.
like definitely in the right place to kind
Absolutely.
of be engaged and continue the great mission work that's happening.
Absolutely. Very nice. Very nice.
Um, but we
Okay.
can jump along here.
Mhm. Let's see.
Yeah, so we can kind of talk top level about the decision tree strategy in and of itself. You know, what is it exactly?
Yeah.
Well, essentially, it is kind of like a roadmap. If we had, say, uh, a search for a really good book, like the analogy, I want to find a really good book that I want to read.
Okay.
How would I find it? I'd probably go to a bookstore. I'd probably pick up a few books, look at the cover, see if the covers are interesting. And only then would I probably turn it around, read the back, and then maybe go through, read a little bit of the introduction, get a little flavoring of the text, and then determine whether or not it's a good book or not. This is
Yeah.
an analogy, by the way, that Jamie Krause came up with.
That's
So
very
again,
good. It's very
another shout out to her. That's really
good.
creative, and I
Yeah.
love the analogy. This is exactly the type of methodology that we employ with the decision tree. It's basically a
Okay.
flow down diagram of decision choices that you make based on the information that's provided in the step above. So to start out with, what are the contextual information that you want to know about the planet?
Right.
Maybe to first order, you want to know whether or not the planet is habitable, meaning it maintains surface conditions that are suitable for life in that it can sustain liquid water on its
Okay.
surface.
Okay.
And finding traces of water vapor in a planet's atmosphere through characterizing its spectra would be sort of that superficial evidence to determine habitability. So that might be the next question. Does it have water or not? And then flowing down from that, what are the secondary observations and questions you might ask in terms of whether or not it might have life that's indicative of Earth-like life?
Okay.
Well, maybe you would make a search for oxygen as the next step. Why? Because what we take a breath right now,
Good.
that's oxygen. 21% of Earth's atmosphere is comprised
Good.
of oxygen.
Good.
It
Good.
is
Good. Good.
a major atmospheric constituent,
Mhm.
and it's predominantly produced by photosynthetic, biologically driven processes here on Earth.
Blue
And
green algae.
so that might be the next tier, the next step in your decision-making process. And
Hmm.
so that's the gist of it, is kind of going through and picking out what is the step-by-step flow and framework that you would order your observations and then make the next decision, the next observation based on information that you derive and obtain
Ah,
prior.
okay.
So
Cool.
being able to organize this into the decision tree strategy framework helps us contextualize, again, the questions that we would want to ask for a given target
Hmm.
and really start to be able to triage planets into different categories. Could
Nice.
it be more Earth-like versus Archean Earth-like, where these two vastly different eras of Earth's history and geological time
Yes.
present themselves very differently in the way that their atmospheric signatures would have been presented, and therefore their atmospheric spectra would be characterized.
Yeah.
And so you'd have a different set of questions, and you'd categorize it differently accordingly.
Nice.
So that is the decision strategy
With you.
top level.
Mm-hmm.
Uh, we can keep going down here.
Okay.
A lot of this is just really intricate detailing of the decision tree itself, where
Mhm.
if we look, say, on the right-hand side, where we're looking at band passes, 1.5 to 1.8 micron band pass, that provides context for species like methane and CO2 in a given atmosphere, because this is where these species
Sure.
absorb within the operating wavelength range for HWO. So we're really considering a strict wavelength range from around zero point 0.2 to 1.8 microns, again, to kind of help facilitate,
Okay.
decisions we might make in terms of what observational ranges do we need for the observatory, and then what features do we want to hone in on really specifically for the decision tree, as this is what we're going after and trying to interpret.
Got it. Okay. Very good. I'm with you. Okay.
Yeah. Great, great. So it kind of brings this in nicely to the
Yeah.
figure, so you
Nice.
can get a visual representation of what I've been talking about in terms of the flow, the organization. And so, like I mentioned earlier in the example, starting with the absolute top of the decision tree would represent your observation in terms of like, this is the start of your characterization step. And within this particular wavelength range, 0.81 to 0.97 microns, we have a wealth of spectral features to go after, including the key question here about water vapor, really determining and confirming its habitability, where presumably we'd have precursor knowledge of these planets. We might say, hey, this planet is orbiting within the habitable zone region of its host star,
Okay.
meaning the distance at which we'd expect surface water to exist. So
Mhm.
maybe it's located in the right place,
Yeah.
orbitally speaking. But now, can we confirm that with actual detections of water vapor in its atmosphere? That's the question. And you could go after that question by observing in that specific wavelength range for
Yeah.
the water vapor. And now you might ask, why is this wavelength range limited? If the observatory itself can observe from zero point 0.2 to 1.8 microns, why not just do it all? Well, the problem there is that, for one, the way coronagraph instrumentation works is that essentially what HWO will do is it will block out light from the host star so that planets that are orbiting around that central star can then be revealed through that starlight suppression.
Okay.
And with the instrumentation and the implementation of a coronagraph, typically it's designed in such a way where you have specific what are called band passes. These are the wavelength ranges that are observationally placed, and you observe in that particular wavelength range. So it's sort of like just that one sliver of the spectrum is going to be visible at that time because you're observing in that particular band pass.
Gotcha.
With that in mind, knowing that coronagraph instrumentation is going to be employed with this observatory, we want to know then, well, how much information can we derive from those small slivers of the spectrum if that's all we're going to have access to at a given
Okay.
time?
Okay.
Knowing that there's room for subsequent observations, follow-up observations, and other band passes that we can then piece together to kind of get a fuller picture.
Nice.
So we asked the question whether or not there's water vapor in this atmosphere. Let's say we take an observation, we see that there's a very prominent water vapor absorption feature, and I'll talk about this more in the next section in terms of the retrieval analysis itself, but let's just jump right to the punchline where we say, okay, we have determined with an X certainty that there's water vapor in this atmosphere. So
Okay.
yes on that box.
Okay.
Now, where do we go from here? Well, let's say that we've detected water vapor, but we haven't detected another species in that wavelength range, methane. So if we haven't detected the methane, we've only detected the water, then
Mm-hmm.
we move down to the second green box in the decision tree framework, which is
Yes.
presents right back to the question and the example I led into earlier, looking for
Oh,
signs of oxygen
yep.
as your next step. And
Cool.
here, what we're really focusing on within this wavelength range is oxygen and the absorption feature at around 0.76 microns, which
Okay.
it's representative of the oxygen A band. It's really strong in this regime, depending on the oxygen abundance that's
Yes.
there.
Yes.
So given that it's one of the strongest features, that's why we chose that particular wavelength regime. And now we want to ask the question whether or not there's oxygen there.
Okay.
And based on that observation, again, based on the retrieval analysis or statistical analyses techniques that you'll employ, you'll decide then whether or not you've found oxygen, if it was a non-detection, or you found a little bit of oxygen, or you found a lot of oxygen.
Okay.
And let's say that you could constrain that oxygen abundance to around, medium levels where it's not so high that you'd expect it to be produced abiotically through water vapor photolysis. You're
Yeah.
losing a lot
Right.
of your water, you're losing your hydrogen, and all the oxygen is left behind. That's representative and indicative of an abiotic process for oxygen production. And that's why labeled it as a dead rocky planet. So
Okay.
the medium here is like the sweet spot between the oxygen is there, it could be another potential biosignature. So let's move into the
Oh,
near infrared
right.
wavelength regime and try to search for other atmospheric species like methane and CO2.
Yep.
These species, like I had mentioned before, predominantly absorbing within this wavelength range at the 1.5 to 1.8 micron range. However, for modern Earth's level of abundances for these species, it
Okay.
actually is really difficult to detect the methane in particular, just right off of the bat, even going to extremely high data quality or data observational quality
Okay.
in terms of the retrievals. So typically we get the non-detection of the methane, but it's okay. We're not dead in as we can try to constrain and understand other atmospheric parameters that might still lead us to a modern Earth-like characterization. In
Right.
particular, we really care about the pressure, and we
Yeah.
care about the pressure because if there is a lack of non-condensable gases in your atmosphere,
Okay.
meaning lack of a background gas like nitrogen,
And Earth.
then again, at low pressures, water vapor can exist at higher altitudes, and there's more potential for it to be photolyzed. So
Mm-hmm.
there is that potential for abiotic oxygen to be generated, and that could be what you might predict or perceive based on the oxygen levels you find. But if you're able to constrain the surface pressure to higher than that zero point 0.1 bar threshold,
Uh-huh.
then you're able to safely rule out that false positive mechanism for abiotic oxygen
Cool.
production.
Okay.
And then you kind of reach to the bottom of the decision tree. Hey, let's triage this planet preliminarily as the modern Earth-like category, and let's really spend all of our resources as much as possible, as
On
much
that
as
one.
yeah, to really hone in on that particular planetary target. And
Got
you
it.
ask these questions for all the planetary targets you have and go as
This is
deep
where you want
down
to end
or
up. Yes.
shallow as you need to in the decision tree process to
Cool.
get to.
Very
Um,
cool.
and
Okay.
I won't belabor this too much, but I'll just say for the sake of since we've included those results in this paper and we'll go over them later, I
Okay.
also highlighted in orange the Archean Earth-like pathway, which
Yes.
again, it's a representative of an epoch in Earth's history that'd be very different from modern Earth. And here we care about the methane because it's more detectable. It's a more reducing atmosphere, so you'd expect so much of it that you might even be able to detect it at visible wavelengths alongside the water vapor feature in
Wow.
one go, which is pretty great. You kind of
Wow.
get two birds with one stone
Yeah.
there. There's
That
a
would be
lot of methane
amazing.
present.
Uh-huh.
Um, so that's the Archean Earth branch too. You'll see results in the paper for that as well. But we
Mhm.
focus on modern Earth first in the paper, and then we present the results for the Archean Earth to really showcase how the decision tree works in practice, and also showing how well do we derive this atmospheric information. And we figure that out by applying the retrieval analyses to it.
Nice. Very good. I'm with you. Great overview. Okay. Cool. Onwards.
Yeah, feel free to
Hmm?
move onwards.
So we do a spectra, or you want to talk about RFAST?
So yeah, let me talk about RFAST first,
Mhm.
and then I'll get into the spectra.
Okay.
So RFAST is the retrieval model that we use in order to facilitate these statistical investigations of each atmospheric case study.
Okay.
So just in general, retrieval modeling is a statistical method in which you can use Bayesian statistical analyses to really understand how well you can extract information
Yeah.
from a given forward model. In this case, our forward model is radiative transfer,
Sure.
which produces the spectrum. So
Yep.
we are using a model that generates a simulated spectrum, and then we match that simulated spectrum to a noisy data set.
Hmm.
And we do an iterative process where we're continuously
Wow.
adjusting the actual input parameters to generate new spectra.
Wow.
And until we reach a statistically good fit or match between the data and the model that we're using, then we know we've sort of achieved the right level of kind of matching or correlating between the data and the forward model. And that helps us understand, well, what is the likelihood? What is the probability that the actual true value for a given parameter is within X range?
Right.
And it'll make more sense when you see examples of this, but they're called parameter posteriors or marginal posterior distributions.
Uh-huh.
And they, in short, represent the uncertainty of a given parameter. Like how well or not well do you know this particular parameter based on how well you've been able to fit the model to the data, essentially.
Cool. I'm with you. Hmm.
Yep. So it's a little bit of a segue, but in terms of oh no, you can go on to the spectral figure. This
Okay.
is a little bit of the segue where we're showing a spectrum of modern Earth, and we're really keying in on the particular band passes that are part of the decision tree
Yeah.
that hone in on each of those different steps.
Wow.
So the really light green box represents the wavelength range, the bandpass for the water vapor. And now you can see exactly how the water vapor features line up within that bandpass. We're going for a really,
Mhm.
really deep one at
Mhm.
0.95 microns. And then we even get for free a smaller absorption feature of water vapor closer to zero point 0.8 microns as well, which is
Yes.
important for mitigating potential pressure degeneracies.
Okay.
Um,
Yeah. Oh, it's even color coded with figure one. Very good. Okay.
Right, yeah, yeah. It's all
Good.
it's
Thank
all
you. Thank
roughly
you.
color coded. You can kind of keep track.
Right.
And that secondary green box within the visible is particularly pertaining to the oxygen A band, like I mentioned, which you can see it's really deep absorption feature for modern Earth-like abundances.
Yep.
That's what you're really honing in on with that secondary band pass, in
Mhm.
addition to getting more water vapor features, because water vapor is plentiful and absorbs a lot of places in
Does.
our reflected light spectrum.
Indeed.
And then color coded in red, you can see the near infrared bandpass
Mhm.
for trying to get as much information as we can from species like methane and carbon dioxide. And then for scale, in terms of the data quality, we've been doing these retrieval analyses by instead of having actual data sets, noisy data sets that we can work with that are real, we created ourselves. We
Uh-huh.
create these noisy data sets, and then we add statistical error bars that are representative of a signal to noise ratio of 10. So that
And
means data quality, you've got 10 times more signal than noise in your data.
hmm.
And that's how big the error bar ends up being.
Hmm. Looks like you
Uh,
don't quite get as much wavelength resolution at longer wavelengths. Is that right?
yes,
This
that
figure?
is true. That
Okay.
is true. Yeah.
Yeah.
For the preliminary observational and like instrumental design for the observatory, it'd
Okay.
be set up with three different coronagraphs, three separate coronagraphs,
Uh-huh.
each with its own resolving power. So
Got it.
7 in the ultraviolet, 140 in the visible, and then 70, roughly 70 in the near infrared.
Okay. Okay.
Yeah, yeah.
Got it.
But yeah, we can move a little bit further
Sure.
along here.
Okay.
So that's how the spectra are split up and
That's
how
spectrum.
we're
Mhm.
setting up the retrievals. So in a given set of observations, we're only seeing that one particular bandpass or a combination of those three bandpasses for modern Earth, and then we're stitching them together into a retrieval analysis to see, well, how well can we constrain the different atmospheric parameters and atmospheric species that are present. So we can scroll down to the next figure if you'd like, which should have our first instances of
Okay.
these parameter posterior distributions.
Zoom out a little bit to get all of it, and we'll zoom in as need be. Okay.
Yeah, of course, of course. So in the top left here, you'll see first and foremost is the parameter and posterior constraints for water vapor.
Okay.
So on the x-axis is the water vapor abundance.
Okay.
And typically when we're reading these plots, a very wide posterior, something that expands that entire range, means we have no idea how much
No
water
clue. Right.
because it could be trace amounts all the way down to e to the minus 10 or water vapor dominated. We're going all the way up to 100% water vapor.
Right, which is right there.
Um,
Yes.
so
Right.
better posteriors essentially indicate a more constrained, tighter distribution that is centered around what we know to be the true value of water vapor in Earth's atmosphere. That's the black dashed line. So
Yeah.
we know we've done a good job when our distributions are both tight, meaning they are very well constrained, and also they're constrained in the right place near the true value. And so it may not be surprising, but for the cases studies where I have retrieved on all three band passes at once,
Okay.
that has given us the best constraints on the water vapor abundance.
Makes
And
sense. Okay.
right, yeah, yeah. It's not surprising because basically, the more information that you have to be able to give the retrieval, the better it will be at being able to constrain a given parameter. And it's especially the case for water vapor because
Yeah.
you saw in that previous plot spectroscopically, the water vapor is absorbing at multiple places. So you're getting additional information by having all three band passes and being able to constrain it. But one other thing that I really want to highlight
All right.
is even with just the singular bandpass that is dedicated to the water vapor,
Okay.
that's the 0.89 bandpass, and that's the blue with the
Uh-huh.
hatched regions.
Pretty
That
good.
is also pretty good. Yes,
Pretty
it's
good.
pretty well peaked, and the spread or the confidence region
Yeah.
for that particular distribution is still kind of within 1 to 2 orders of magnitude
Uh-huh.
to 1 sigma certainty. So you'd still definitely be able to get a strong detection of water, even with just that singular band pass. And I
Um,
think that was a huge takeaway from
yeah.
this paper because before this work, we really didn't know whether or not having such small spectral coverage would be able to be enough
Right. Right.
and do the trick. But now we've kind of demonstrated that, at least for signal to noise ratio 10, which
Yeah.
is modest in terms of data quality, it's doable.
Yes.
And so I think the only other one that I'll cover here is
Okay.
C for the oxygen abundance, because that's the secondary level of the decision tree.
Yes.
And
Dude.
similarly to the water vapor, and really all of the constraints we'll find that more information leads to better constraints on the whatever parameter it is that we're trying to constrain. And that's even the case for the oxygen here, where the all three band does the best in terms of being able to constrain it. We still have issues with, those extending tails toward low values.
Sure. Yes.
But they're certainly beaten down more so for the all three case study. And then I believe the purple one is the oxygen only, but we can scroll up to the
Yes.
oh, okay. So the oxygen and the water vapor band
Yeah.
is
Yeah.
does second best on that
Mm-hmm.
front.
Mm-hmm. That actually does pretty well just in and of itself.
Hmm.
But
Hmm.
yeah. Okay.
Yeah, yeah.
I'm with you. Cool.
But just to shortly go over the methane and CO2, all I'll say about that is that it's challenging. It's really
Wow. That's
tricky.
really wide.
It's really tricky to get the methane because the abundances are so low. They're at ppm level,
Right,
so
right.
parts per million, or 10 to the minus 6 in terms of
Uh,
ratio. So it's not a very dominant species in Earth's atmosphere, which is why it's so tricky to both see the spectral feature in reflected light and try to constrain the abundances here. But I guess what I point out and outline with this particular one is that it's not only about detecting the abundance of a given species, but it might also be your goal just to differentiate from one type of planet to another.
yeah,
So in this case, if we take a very optimistic estimate for how much methane we would expect for an Archean Earth-like
right.
atmosphere,
Uh-huh.
then presumably we could at least tell the difference and say, well, with the all three bandpass case, which again does the best, that posterior distribution is not even overlapping with the
Right,
Archean Earth-like estimates
right.
for.
Halo.
So
Hmm.
maybe we could discriminate between Earth-like planets versus Archean Earth-like planets.
Yeah, even if it's binary, right? Yes or no. I mean,
Yes, exactly. It's like
it-
that's still
it's
information.
still
That's
info,
good
yeah.
information to have.
Hmm.
So that's the advantage there for the methane.
CH4, and then we got CO2, and that's even wider.
Yeah, it's tricky.
Yeah, yeah. Wow, yeah, even all three sort of can't really distinguish there. But again, it's you can get a binary out of it. Yeah.
hmm hmm
Okay.
But yeah, feel free to scroll on down.
Yeah. I just losing myself in that figure. Okay, figure four.
Oh yeah, of course. Yeah, you can take your time too. Don't mean to
Good.
rush.
All good. All good. Okay, figure four.
So we did a parameter sweep well, we had included a lot of different retrieved parameters in this study, including things like the surface albedo or the level of
Yeah,
reflectance of a given planet,
there it is. Okay.
planetary radius,
Mhm.
and mass as well. We're not really too surprised about the lack of constraints on the mass per se, and
Ooh,
we sort
yeah.
of chalk that up uh, to, well, maybe we'd have precursor observations that be better suited for determining some of these bulk planetary properties that maybe we could use precursor information
Right.
to then better constrain these types of parameters on the back end. But just interesting to see how well or unwell we do given the information that we have, because again, we're only working with limited wavelength ranges and limited bandwidths of observations. So
Still do pretty
that's
good on the
good.
radius. Radius is pretty good.
Yeah, yeah, we're still doing well on the radius. I think most of the radius constraints stem from the fact that we are holding these observations at a particular phase angle. So when we know the phase angle of the
Okay.
planet,
Okay.
then we can better constrain the radius because it can only be that bright if we're absorbing at
At
a
some
certain
angle.
phase.
Right.
Yeah, yeah.
Yeah.
Um,
Good. That makes sense. All right. Mm-hmm.
but
Cool.
that is it for the bulk planetary parameters. We can move on down to the what I call the planetary parameters for the pressure
Pressure
and the
temperature.
temperature.
Uh-huh.
And of course, you'll remember that pressure is really important because
Good.
since we have a lack of constraints on the methane abundance, we really want to be able to low out the low pressure regime
Mm-hmm.
in order to mitigate and rule out potential false positives for oxygen. And as you can see on the low end, um, we have very low likelihood for those low sort of zero point 0.1 well, in pascals, we're kind of going toward like one and log scale,
Yes.
trying to rule out 1 to 2 in terms of the log scale for the low pressure end.
I'm with you.
Um, and you can see that constraints that we get on the pressure are nicely peaked. They're
Mhm.
consistent with the true value. And this was really interesting result for us because if you notice, so in the original spectral plot,
Yes.
We are not covering, and we don't have a specific bandpass that covers the Rayleigh scattering slope.
Right, which was on the short end. Uh-huh. Hmm.
Yes, exactly, exactly. But we're still able to place reasonably good constraints on the pressure because we're also able to constrain the water really well. And so these sort of dominant effects that are related to like pressure broadening can sort of help us in this realm where we're gathering the pressure information from the water vapor as opposed to, yeah, being sensitive to the specific Rayleigh scattering slope.
Yes, exactly.
Those.
Okay, I just wanted to slide up to remind what the Rayleigh.
Right, yeah, to show where it is.
Yeah.
Yep, exactly, exactly.
So even the 0.89 does a pretty good job. It's a little off center. It's got about the same width. It's not terrible.
Right. Yeah. Yeah, it's nicely peaked. I'd say, the 1 sigma widths are again going to be on like an order of magnitude or so.
Yeah.
Um, so it does well, even with a singular band pass. And it would certainly be enough. It'd be enough contextual information to rule out the false positive because we really don't see any tails extending to low values. They're not very prominent in any of the combinations.
I would say this 1.65er really likes high pressures.
Yeah,
Big
yeah,
spike out there. 8. Wow. Okay.
yeah. And that's just working with information from the near infrared wavelength range. So,
Very cool. Okay, so we got the pressure, the temperature, we got the radius pretty well. That's pretty good info. Okay.
mhm. Yeah, yeah. And having such great temperature constraints, again, is just kind of cherry on top. We didn't really expect this to come about in this work because we were really focused on the parameters that are included in the decision tree. But again, water vapor is a dominant species in our atmosphere. And so its opacity, the amount of light that it actually blocks out,
Yes.
is also temperature dependent.
Yeah.
So again, having really good constraints on the water vapor here because it's a bulk species in the atmosphere also helps us with constraining some of these other thermodynamic parameters as well, like the temperature. So
So
that
just to be
was
totally, so the pressure here is at the surface and
correct.
temperature is also at the surface, or is that at the optical depth of one?
It's also at the surface.
Surface. Okay.
Yeah.
Okay.
Hmm.
Thank you.
Yep. Absolutely. Absolutely.
Okay.
And that pretty much concludes the results for the modern Earth-like pathway. You can
Okay.
see now the flow of the decisions we made, where we got the water vapor abundance really well constrained. We got the oxygen abundance constrained, depending on the wavelength coverage. But we'll say we had all three
Let's
band
say we had
caps
all
covered.
three. Yeah.
We got it. And with that, we didn't get the methane, but we got the pressure. So we
Yes.
navigated through the decision
Very,
successfully to be able to kind of make those trade-offs. And again, as limited number of observations as possible, and we didn't even do the full wavelength range or the full coverage that we would have access to.
or stacking multiple years, multiple observations on top, etc. Yeah.
Right, exactly,
Yeah.
exactly. This is
Okay.
just to get out the gate.
Yep. Absolutely.
Um,
Very good. Cool.
And the last result that is associated with the modern Earth results is just a different representation of the results because now we're looking at the bandpass combinations separately and then how each of the species abundances do against each other and how well we can constrain each one just per bandpass configuration. So it's just another flavor of
Mhm.
presenting that information.
Yes, we have peaks where we would expect them and long tails in some cases.
Hmm.
Yep,
Yeah,
yep,
yeah.
yep. Okay, good.
So we can move into the Archean Earth results if
Good.
you'd like.
Now let's go into
Um,
early Earths.
yes, an earlier epoch of Earth where it's representative of much more reduced conditions. You can see things like the oxygen and the ozone features are basically non-existent because it's not an anoxic atmosphere. But
Right.
you really key in on the fact that there is now a methane absorption feature, or right where you'd also have the water vapor feature around 0.89 microns.
Yes.
So that is the same bandpass that we'd use for modern Earth. We can use it for Archean Earth, get a different set of information and hopefully be able to discriminate between the two. And I'll note that these are haze-free atmospheric cases of Archean Earth. And all of these atmospheric cases, by the way, are run and generated with a photochemical climate model called Atmos.
Uh-huh.
Um,
That was up here.
right, yeah.
Somewhere up here. I remember rolling
It'll
back.
probably be in the methods with like a separate subsection
Atmos. There we go.
for it. But yeah, it essentially, self-consistently models each of these different atmospheric cases by taking into account things like the initial abundances and reactionary pathways for different species in the atmospheres, boundary conditions, whether or not you have outgassing at the surface or you want to keep it fixed at a given mixing ratio.
Oh,
Then
right.
it calculates what you'd expect at equilibrium for all of these species by calculating its total production and loss rates and then equalizing that to its final steady state. And then you can couple that photochemical modeling scheme with the climate model that's also part of Atmos. And that will help you better constrain and get a better idea of what the temperature pressure profile should look like with that specific chemical composition for the atmosphere.
Yes. Okay. Nice
Yeah.
shout out to Atmos there. Okay.
Yeah. Thanks for letting me go back on
Yeah, I
that.
just wanted to go back because I saw it and I said, okay, well, we'll come back to it. Okay. Where were we? Oh, we were on
And
spectrum. Okay.
right. Yeah. Yeah. So we have the two band passes for the Archean Earth, and we've got that band pass in the visible to get at the water vapor and the methane abundance. And
Hmm.
then here in the near infrared, you can see the methane abundance, or the methane absorption feature, I should say, is
Yeah.
much stronger here because we have much more methane in comparison to the modern Earth case,
Yes.
and more CO2 as well. Both features are um, much more visually present in the spectrum.
Yep.
We can see them.
Cool. Cool.
Again, all of these retrieval results are done with a signal to noise ratio or data quality of
Mhm.
10.
Mhm.
And these retrievals were really easy because it's just two band passes and
Yes.
one individually, and then you do them both. So
Okay.
these posteriors will
Life
be,
simplifies this way.
yeah, yeah, exactly, exactly. Much more simplified.
Okay.
Um, and so the key takeaways for these results, again, what we want in a first precursor observation for characterization is we want to be able to get the water vapor and the methane,
Yeah.
presumably in one go. And that's achieved with the 0.89 micron bandpass, even if you just had an observation there, getting
Yeah.
nice peaked distributions.
Yeah.
Round truth for the water vapor and methane, albeit the water vapor is biased a little bit low, but nonetheless, these be
Close.
representative of a strong detection of the water vapor in this case.
Right.
We really do have that advantage here of kind of killing two birds with one stone with that singular bandpass region. And then for the CO2, we did find that the retrieval model was struggling to detect CO2 at a signal to noise ratio of 10, just because you can see those tails extending to low values.
Right.
It's trying to make a detection at the bandpass combination that includes both of them, so the 0.89 bandpass and the 1.65 bandpass, probably to be able to try to rule out other sort of atmospheric scenarios that are indicative of that low CO2 that CO2 abundance. But it was still struggling. And
Okay.
so we really wanted to see, well, with the singular band pass, so just the 1.65,
Hmm.
how high do we have to crank up the data quality to be able
Mm.
to achieve the CO2 detection? And it looked like at a signal to noise ratio of 20, now
Okay.
we're able to kind of remove those tails, extend those
Ah, here we go.
statistically significant tails extending to low values.
I like it.
And that's how you could presumably achieve the CO2 detection.
Okay. Nice. Nice. Okay. I'm with you. And now the dashed lines are appropriately for Anarchy on Earth. Yeah.
Yeah, for an Archean
Okay.
Earth-like
Okay.
atmospheric scenario.
Checking.
Yes.
Just checking. Okay.
Yeah.
Cool.
Yeah. And so now we can kind of scroll down. All of these figures that we saw for the modern Earth case are going to be repeated for the Archean Earth case. Just
Good.
looking at the planetary bulk parameters, again, lack of constraints on surface albedo and things like planetary mass. Again, pretty good constraints
Yes.
on radius
Yeah, we
for
still
the
got
same
some.
reasons.
Okay.
Yeah.
Okay. Yeah, it didn't suddenly magically get better in the mass because we changed the atmosphere, right?
Yeah, exactly. That
You
it
know,
doesn't.
that ain't gonna do it. If it did, I would raise my eyeball. Okay, very cool. Very cool. Okay, nine. And let's slide down
Let's see the
to
thermal parameters
oh yeah, this is thermal.
here.
Okay, pressure's a little wider.
Yeah, the pressure is a little bit broader for the 0.89 and
Hmm.
1.65 scenario.
So,
Um, but it was kind of interesting that the singular bandpass observation does a little bit better. Again, it's tied to the water vapor abundance and constraints you can place on the water vapor.
hmm.
And so that's where we're getting the information. So that's kind of helpful in constraining the pressure in that sense. And then the temperature constraints are fairly similar to the modern Earth-like constraints.
Yeah.
Again, kind of tied to the water vapor there.
In blue. Yep. Yep. Okay. All right. So we can get both. We can get both modern Earth and we can get Archeans. Very good. And here we
Yeah, we're
yes.
categorizing them pretty well. They're pretty distinctive from one another, which is great.
Like
And
this
this
picture
is
abundance.
another repeated representation, so you can see all the species abundances and their constraints all in one plot, sort of
I like that.
separated out by the bandpass configuration.
Okay.
And we've got exactly what we want in terms of achieving constraints on the water vapor and the methane abundances as well. And then CO2 in the right sort of regime of observational quality, because these are still just the SNR 10 results. But
Yep.
if we had SNR 20, then we'd be able
You'd
to
be
get that as well.
really good. Or better, I should say. Nice. Okay. Very cool. And let's see where we go. And we off with some conclusions. There's a couple of awesome appendices you should check out, people.
Yeah. If you want to see sort of a numerical representation of the uncertainties, you can check out the appendix. Each of the parameters are listed with their 1 sigma uncertainties, and then every bandpass combination for each of the two atmospheric cases that we did, the modern Earth and the Archean Earth.
Right. So do check that out. Okay.
That is pretty much it.
That was very nice, Amber. Very cool. Very nice. Okay. Amber, I want to thank you so much for walking us through your very awesome PSJ article. Very cool.
Oh, thank you so much for giving me the opportunity. Appreciate it.
Sure. Let's see. And let me ask a little bit. You did mention that HWO was, on the order of 10, 20 years off. And this was sort of a preliminary study on where we might go on, once we detect this, that, or the other in a decision tree to follow. And so where do you think we go from here, given the published article? Can or should, I guess that's two separate questions. Should the decision tree get more complicated, right? Can we add more lines, make more branch points in the decision? Uh, are there mock observations that could be done, maybe with something else to help, put the decision tree to the test on something, um, like the solar system? I don't know. But just sort of next steps. Where do you think we go from here, given the published article?
Great. Yeah, those are really, really great sort of thought points because a lot of people bring up, how do we adapt the decision tree or build on it? And, my answer has always been that, of course, the decision tree could be adapted. It could be modified because if you're trying to, say, characterize a sub-Neptune planet, just for instance, you
Oh,
might have a totally separate list of
oh
questions
yeah. Oh yeah, yeah,
and
yeah.
parameters that you'd care about. And then you could organize the decision tree to help organize the flow and thought process for what observations you'd want and how you'd actually prioritize them.
Mhm.
Um, So that's
Makes sense.
certainly an area of future work where we want to be able to expand the decision tree, maybe even make multiple iterations of it so that it can characterize other planetary types. Because one of the advantages for HWO is that even though the contrast ratios for terrestrial planets are low, difficult to do,
Sure.
you by achieving that level of difficulty, you get all of the brighter, bigger planets that could be existing in that system, presumably for free.
Yes.
So, we don't just care about the Earth-like planets. When we're thinking about HWO, we care about the entire planetary
Um,
family
yep,
that could exist for a
yep.
particular system. So broadening the decision tree to encompass those is certainly a route we want to go down.
Nice.
Another thing that I wanted to plug too is the fact that a group that I'm leading within Goddard, it's called a scientific task group.
Uh-huh.
And this is an exoplanet collaboration hub that I'm leading to try and bring the exoplanet community together. Maybe they're focused on a particular mission, like JWST versus Hab Worlds versus Roman, but we don't necessarily always have the opportunity to have the same space to talk to each other.
Right.
And I think now's a perfect time to start communicating with one another and outlining, well, what are the next steps for exoplanet characterization in general? Is there another mission that could be follow up, even beyond HWO, that we want to prepare for? And I think the decision tree helps us with starting to articulate those questions. What are we interested in knowing? And kind of going from there. So, this STG is also sort of a follow on bridge to that work. And I encourage you to reach out if there's any way to get my email or post it
Well, if you
alongside the
made
video.
available. I don't want to put your email in a description below video. That might be a bit
Oh,
much,
sure. Yeah.
but
Understandable. If
well,
we
we
ever
will
want to
certainly,
pull,
get the word out. So join that SPG, people.
yeah, absolutely. Absolutely. Like,
Very cool. Good advertising.
it's a
That
good
was
job.
great. Very good. Amber, I want to thank you so much for walking us through your very awesome article again. Very nice. Thank you.
Yeah, thank you so much for having me. Bye,
Yeah.
everyone.
And that'll do, everyone. And I hope this made your astronomy exoplanet day just a little bit better. And we will see you on the next one. Bye bye.